Hello dear students. In the last video we saw that how we can calculate colligative properties and from help of colligative properties we can calculate molecular mass except when the solute molecules either undergo association or dissociation. Solute molecules like acetic acid stay as dimer, two molecules stay together due to hydrogen bonding, and solid molecules like sodium chloride, they stay dissociated because they are ionic compounds, so they stay as sodium ion and chloride ion. In both the cases, you cannot calculate molecular mass with help of colligative properties correctly because colligative properties depend upon number of particles. And you can see here that number of particles in case of association is becoming half, right? It is 2 here, while here it is 1 dimer. So when you are measuring the colligative property, it will count as 1 particle, not 2 particles. In case of sodium chloride, you can see that resultant is 2 particles. Therefore, the colligative property in case of acetic acid will become half, and in case of sodium chloride it will become double. In that case, the molecular mass of acetic acid will come as double, and in case of sodium chloride it will come as half. So to take care of this anomaly, Van't-Hoff introduced a new factor I, where I can be given as total number of molecules of particles after association or dissociation divided by number of moles of particles before association or dissociation. And if we include this Van't-Hoff factor into the formulas that we saw in the last video, the colligative formulas can be given as relative lowering of vapor pressure can be given as I small n by capital N. Elevation of boiling point can be given as I kbm. Depression of freezing point can be given as I kfm, and pi, that is osmotic pressure, can be given as I nRT by V. Now question is how to calculate I. As you saw in the previous slide, that I is the ratio of observed particles, observed number of particles, and calculate number of particles. Now we are going to see that how to calculate this observed number of moles of particles. In case of association, sorry, here this I should have written association, so let me correct it. Association. In case of association, as we discussed, that number of moles become half. Let's see, at time 0, if we take acetic acid 1 mole and dimer is 0 mole. Okay. After time t, when equilibrium has been attained, x moles, x here is the degree of association. X moles out of 1 mole undergo association, and therefore you can see that number of moles that will appear by combination of x moles will be x by 2. And if you calculate total number of moles, it will be this plus this, that is 1 minus x plus x by x, which is 1 minus x by 2. In case of association, it can be given as 1 minus x by 2 divided by 1. Van't-Hoff factor can be calculated like this. Now questions, numericals are can be formed mainly in two forms. Number one is either you will be given the change in colligative property and you will have to calculate I. From that I you will have to calculate degree of dissociation or association, or you would be given degree of association or dissociation and you will be having to calculate change in colligative property. So this was total number of moles of particles when there is association, where x is degree of association. Now in the next slide we come to the end after looking that when we are taking a solute like sodium chloride where it dissociates, x is degree of dissociation, and like we did in the previous slide at time t where equilibrium has been attained, X moles of sodium chloride dissociate into X sodium ions and X chloride ions. Now in this case, total number of moles will become 1 minus X plus X plus X, that is 1 plus X, and therefore I can be given as 1 plus X by 1. So I hope you have understood this well and it was beneficial for you. If you like this video, please subscribe and press the bell icon. I will be coming with a new video very soon. Thank you so much. Bye bye.